Okay, welcome to another Orbiter 2010 video. And in this video, we're back here on the moon, and we're going to continue this this explanation of how to go from the moon to drop down to the Earth to get that gravitational sling and then go off to another planet. In the last video, I did quite a bit of explaining there at the beginning, and then we went through the basic, the first part of the setup process. But when you go through this process, you run into a point where you have to do at least 2 levels of refinement, and sometimes 3. And I suppose in extreme cases, you might even have like 4 levels of refinement. It may seem meticulous, it may seem like overly complicated, but it's actually not. And once you learn the process, once you have it memorized, you can actually go through it very quickly. I went through this again last night. I did 2 quick example flights just to make sure that I was familiar enough with the process to be able to sit here and record this video today. And after I did it 2 times, I was just very fast at it. So as you watch this explanation, and it seems to go on for a long time, that's just because I'm trying to explain everything and make sure I don't leave out any details. But when you start memorizing it and doing it yourself, it's much easier. All right, let's switch camera views. So when we left off, we were at, we had the moon at a 90-degree position to the antipode for where we are, going to where we need to be in order to drop back to Earth and be at Earth's periapsis at the proper time. But when we did our date adjustment, you can see it changed the shape, or changed the position of this line here, which indicates that we can no longer use this line here because it's no longer halfway between this point and this point. So we're basically going to start over in a sense, but this time it'll be faster because we don't have as much refinement to do. The way we start over is we go to scale to view and we change that from craft to target. And you can see the lines like that. We just simply need to adjust it here. Let me turn that lock off. And we just need to adjust it so that it's lying over top of that yellow line. And again, in a perfect world, if you lay it exactly correctly, you won't be able to see any yellow pixels if you get it laid down exactly correct. But it doesn't have to be that perfect. I mean, if like this is fine, but if you want to be just a little bit more picky about it, like there is even a little bit better. And if we kind of maybe bump it up just 1 more pixel, that's pretty good there. I can see several pixels, so it's not exactly perfect, but again, it's trust me, it's good enough. So now we'll press ++ to go scale to view back to craft. And you can see now that the moon, or rather now the line is, once again, it's halfway between here and here. But now we are greater than 90 degrees away from this point. We have a couple of options. One option would be to bring ourselves back to where we're 90 degrees away from the antipode and then do the calculation again. I don't think that's probably necessary. What we can do is we can kind of shortcut it a little bit. And instead of going to 90 degrees, we're going to go to 45 this time. And again, I'm just going to eyeball that. And I'm going to say that 45 degrees is going to be about right. Maybe, so 90 would be about here. So 45 would probably be when the moon is between the O and the O here. So let's just fast forward time. And I'm going to come back out of time warp. And that's just eyeballing it. And I think, and Dimitri explained to me, again, that people are pretty good at estimating closely, a 90-degree angle or a 45-degree angle. We can kind of just sort of visualize these things like a pizza slice or a pie slice. But to kind of just test my own visual acuity, I'm going to bring up that angle tool again. And I'm just going to lay that line there. I won't worry about being terribly precise with it. There, and we'll put it on the moon. So that's line 1. Then where it's at, line 2. And I came up with 50.64. So I actually wasn't that great on that. Let me go ahead and get a little bit closer. That's good enough, but if we want to be a little bit more precise, we need to fast forward time a little bit. And that's probably closer to 45 degrees there. So I can close that out. We don't need it. And actually, let me just test that angle real quick too, out of curiosity. Let's put that there. And first line goes where the moon is at right now, and the second line goes where it needs to be. And now we have a 47.34 degrees, so it's still a little bit long, but that's fine. So the first visualization that you do is at 90 degrees, then the second visualization that you do is at 45 degrees. And why do we use these numbers? Well, again, 90 degrees lets us know when we're a quarter of an orbit away, so that's simply 7 days. And then 45 degrees is 3.5 days. So it just gives us easy ways to calculate the eject date without having to rely on more precise calculations. So we're going to say that even though I know it's 47 degrees, we're going to say it's 45. So from this point to this point is 3.5 days. And then again, from here to here, from the moon to the Earth is 5 days. So I now need the eject date to be 8.5 days from right now. Okay. Now, do you understand why it's 8.5? Let me run through it again. We are 45 degrees away from this point. It takes the moon about 28.32 days to go around one time. So half of that's 14. Half of a half is 7, and then half of a half of a half, which would be half of 7, would be 3.5. So from here to here, it's going to take 3.5 days for the moon to go from here to here. Then it's going to take us 5 days to go from the moon to Earth's periapsis. So 5 plus 3.5 is 8.5. So if we add 8.5 to the date, this date right here, then we know what the eject date needs to be. Now that's adding in decimals is something I can't do in my head very well. So 57138.9 is good enough. We don't have to worry about the last 3 decimals. Plus 8.5 is 57147.4. So our new eject date is 57147. And it's going to disturb this alignment again, but you'll notice that it's much closer now. We're less than now we're just 24 hours off, whereas the first time we went through this, we were off by, what was it, like 14 days or something. It was a lot. So just with one level of refinement, we've gone from an error of like 14 days down to an error of about 24 hours. So 57147.4, that's going to be our new eject date. So we go to a medium setting and 57147.4. And of course, as we do that, again, it disturbs our closest approach. We can see we're no longer seeing Venus in the encounter view. Way we fix that is we just go back to our variables and we just see what we have to do to bring the closest approach back down. Let's see if we can start by taking out some outward. And that seems to be helping. Seems to be helping a lot, and that might be all we have to do. And we hit our low point, so now let's go to prograde and see what we need to do here. Go down to super. I'm seeing 31 is the lowest there, so let's go back to outward. Go down to a super setting, and so it looks like maybe if we overshoot outward a little bit this way, then come back with prograde, yeah, that brings it down. A little bit more on the outward. And that's going to be us basically hitting the planet again. Yeah, we are. Okay, so now that's like level 1 refinement, level 2 refinement. And that may be all we need to do, but we can check. Since we did make a change to the date, we made a change to the eject date, it will have had some impact on this, on where our periapsis needs to be. Now we can just simply plus over to scale to view target to see how far off it is. And we can see that it changed by almost nothing, like almost nothing. If we want, we can fly the plan as is, but because it's Venus, and this would be especially true for Mercury, I would probably recommend one more level of refinement. If we were going to Mars or out to the outer planets, I wouldn't worry about it. But since we're coming in toward the sun, things just need to be a little bit more precise. So let's go ahead and just line this up one more time. I'm just going to lay that line so it's perfectly over top the yellow and there's no pixels showing. That's pretty close right there. Now we're going to come plus plus, and we're going to just cut this angle in half again. So instead of 45 degrees, we'll have, 22 or something like that. So, and that's going to be when the moon is about, you can really eyeball this quite well now because we have this line here, and you can see that from there to there is bigger than from here to here. So the moon needs to be probably about right there. So let's fast forward to that point. And I overshot that a little bit. But that's basically now we are like a day and a half. And I can actually calculate how far away I am from this point. And the way I can do that, we do have to know the angle to do this, but this is something else that I wanted to show in this video. So let's get the angle, however you want to go about getting the angle. Start by putting this line here, and the first line goes on the moon's current position, and the second line goes on where it needs to be. And we now have an angle of 23.05 degrees. Now I made this little sort of sheet here so I could explain this calculation. So the number of degrees until the moon reaches antipode is 23.05. And we need to take that number and divide it by 360. So 23.05 divided by 360 is that number, which I'll write in here. 0.06402. We'll that's enough decimal points. Now we take that number and multiply it by 27.32. And the reason for the 360 here is because there's 360 degrees in a circle. So we need to know we need to divide by the 360 to get the 0.06402. Now we take that and multiply that times the number of days it takes the moon to orbit the Earth one time, which is 27.32, not 28.32. So 0.06402 times 27.32, and that's 1.749. And that is the number of days. This is the number of days that it's going to take the moon to go from where it's at right now. Excuse me. The number of days it's going to take the moon to go from where it's at right now to this antipode position. Remember, when it was at 90 degrees, it was going to take 7 days, and we could just do that quickly in our head. And when it was at 45 degrees, it was 3.5. But now that we're getting to where the angles are less and less, it kind of helps if you can calculate how long it's going to take, using the actual number of degrees. So we're 23.05. So it's going to take 1.749 days for the moon to reach that point. Now we need to know what the current MJD is, and the current MJD is 57140.97 is good enough. And if we add these together, we add the current date plus 1.749 days. Let's just add those together. And we have 57142.719. Let me write that in down here. And this is when the moon will reach antipode. Okay, so in other words, at 57142.719, that's going to be when the moon is at that point. But we need to add 5 more days to that because we have to account for the time that it's going to take us to fall from the moon back to the Earth. So the last part of that is to add 5 days to that number, which we don't have to use a calculator for. We can just say 57147.719, and that's going to be our eject date. And I'll put this sheet, I'll make it available, and I'll put it in the description down below, so check for the link so you can see how this all works. And by watching the video and having the sheet available, you can do this calculation quite easily. So this is our eject date. Our new eject date is 57147.719. Let's check that in orbiter. 57147.719. So we're really close, but we do need to change it a little bit. So we'll go forward to 719, do an adjustment, and that's good enough. You know, the last couple decimal points aren't that particular. But again, every time you make a change to the date, your closest approach, you know, goes all out of whack. So you'll have to go through the other variables and make changes accordingly. And it seemed before that taking weight outward right away was helping. So let's try that again. Yeah, just taking out some outward and we're basically hitting the planet again. So it's good enough there. A little bit of prograde just to get things down even more. I must have went the wrong way with the prograde, so let's change that. Okay, that's the low point there, so outward. Okay, like that. And there we go. Now I think we're hitting the planet again, and we are. Okay, so now we are just 1.7 days away from the time to leave. And we know that that our eject date, you know, we have our eject date figured out here. So we don't really need to do any more refinement. If you really wanted to be absolutely crazy about it, you could cut this in half again. But at this point, it isn't necessary. Now, I will explain briefly. The reason that we have to do 2 or 3 levels of refinement is because the moon does not orbit the Earth in a perfect circle. I'm going to have to pause the video. I have to take that call. I'm sorry. Okay, back again. Sorry about the phone call interruption, but I have just a lot of medical stuff going on, and when the phone rings, I have to pick it up. It's always a doctor or a pharmacy calling. Anyway, again, the reason that we have to do these different levels of refinement is because the moon does not orbit the Earth in a perfect circle. When we say that we're 90 degrees away from this point, we can estimate that that's 7 days out. That's a good estimation, but it's not perfect. It depends basically if the moon is at apoapsis or if it's at periapsis. If it's at periapsis, it's going to move a little bit faster. If it's at apoapsis or close to it, it's going to move a little bit slower. So when we're at a 90-degree angle and we estimate that the moon's going to be 7 days away from this point, it's only an estimate. And then we can do it again when we're at 45 degrees, and then the estimate's a little bit closer because now we're only 3.5 days out. But again, the 3.5 days still has some margin for error because the moon doesn't move at a constant velocity around the Earth. It changes its velocity as it reaches periapsis and apoapsis, or perigee and apogee as it would be around the Earth. So the second level of refinement just helps us correct any errors that we had when we were doing our estimate at 90 degrees. So then we do the second one, and then again, it doesn't hurt to do a third one. You can see that we had a bit of a change there. It wasn't much, but it was a few hours. And when you're going in toward the sun, a few hours can make a big difference, especially if you're going to Mercury. I would imagine if I set this up for Mercury, which I haven't done yet, I would probably do another level of refinement, like even when I got down to this point. So that's just kind of an explanation of why we have to do this in so many steps. All right, we are done with that angle, so let me close that out so it's not in the way. And we are now ready to set up the next part of the plan here. So before we go any farther, what we really want to do is we need to go ahead and warp time forward until the moon is basically laying straight underneath of that line. And it's okay to take it all the way to that point. You don't have to leave any room ahead of time, and I'll explain why in a minute. So for the next part, the plan, we're just going to warp time forward quickly but carefully. And we're just going to lay it straight underneath of that line, and basically we won't be able to see the blue line. And that's good enough right there. You can still see a few blue pixels, but essentially we are where we need to be. The date is 57142949, and we're going to leave in 0.15 from now, which is why it's okay to bring the line all the way so that it's underneath of that line. But before we do, we have to set up the next part of our plan, which is how are we going to get back to the Earth. And we cannot actually do that in this single instance of TransX. So we have to open a second instance of TransX, and we can actually close that line out. We don't need it anymore. So if you don't have the newer version of TransX that has 2 instances that comes with it, then you definitely need to get it. So bring up TransX 2, and you can clearly see, we've got TransX version 1 over here and TransX, instance 2 over here. And for this part, it's really simple. We're just going to set up a simple plan to get back to the Earth. So plus to go to escape, forward on this side, and you can clearly see that this one's red, that one's blue, so we know that we're working with the other instance. And we're just going to VW over to the eject plan. We're going to put in the amount of negative prograde that's necessary to get back to the Earth. When you get down to that point, it helps to go to the setup and change your scale to view to target, and then go back to eject plan and just dial in the last little bit of negative prograde. Now you can see that hypothetical line coming down, and we're just going to bring it all the way down to about there. It's good enough. Now VW back over to setup and change the scale to view back to craft. Now we want to go back on this side, VW to the escape plan, set our PE distance to the number that we always use, which is 1758 E3. And again, the E3 is just a shortcut. And let's go to VW to set up here and change the things that we would usually change. Graph projection over to plan, and scale to view. I think it helps to have it on target. VW back over to the escape plan, and now we want to set our eject orientation. And I'm going through this quickly because this is the stuff that we always do when we go from the Earth to the Moon. This is nothing new. And I always prefer the short way out. Just takes less time, basically. So if we leave here, we're going to have a quarter of an orbit until we eject and go back to the Earth. Again, if you want, you can swing it around the other way, and it looked like you'd be leaving about here. Then you'd go all the way around the moon and eject out that way. All right, we are almost ready to go. What we need to do now, though, is I don't completely understand this particular point, but you don't want to leave right when the moon is underneath of that antipode point. It works out that you arrive at Earth. Your timing is a little bit better if you leave 0.15 after that point, which is like a quarter of a day. So if we simply take, we don't even have to put in all those numbers, but the last number, let's put in the last few digits there. Let me just type in the whole thing. 57142.917 plus 0.15. So we're actually going to leave the moon at 57143.067. And again, I don't completely understand the reason for that. Dimitri tried to explain it to me a couple times, but I'm just missing the point. But it has something to do with your arrival at Earth. When we leave the moon, if we leave at exactly that antipode position where, the moon came underneath that red line, if we leave at exactly that point, we're going to arrive at Earth a little bit early. And it just means that when we do our burn to go out to the other planet, Venus, Mars, wherever we're going, that burn's going to happen before we actually reach periapsis at Earth, and it's just inefficient. We really want to time it so that we arrive at Earth right at periapsis, so that when we do our burn, we are as close to periapsis as we can possibly be. It's never going to be perfect, but the closer we are to periapsis, the better off we are. And by adding in that additional 0.15 and then leaving it that time instead, that somehow helps with the timing. And again, I don't really completely understand it myself, but Dimitri explained it to me that way, and I take his word for it. Okay, I'm actually not sure where I'm at on this part of the video due to the interruptions, so I'm going to go ahead and stop this part here because it's a good stopping point. And I'm going to Control S to save just in case orbiter crashes or something like that. And when I come back, we're going to get up off the moon and head back to Earth. And there's still quite a bit more to this whole process. Even though this part of the explanation, there's still more to know as far as how to finish this all up, how to set this up. So we definitely need to have more explanation. If you like this part of the video, like it. If you didn't like it, don't like it. Subscribe to the channel if you're not already subscribed. Please check the description down below for links. I've got an FAQ that people don't ever seem to notice, and they ask me the same questions all the time, and I just point them to my FAQ anyway. And I've got a Facebook page, and there could be other various links in the description below, so check that out, and I will see you in the next part.